Let's work some examples using the direct comparison test. Our first is 3 to the n over 4 to the n plus 5. So what we want to do every time we're doing the direct comparison test is we want to say, all right, let's take this sequence and let's turn it into something simpler. Let's just use inequalities to make this a more manageable sequence, so therefore a more manageable series. So when doing this, you say, okay, is this less than or equal to something that I need to worry about? And the answer in this case is no, because it's just 3 to the n. The reason why I say no is because if you look at this, I've got a 3 to the n and the 4 to the n. So what I'd really like to do is kind of have something that looks a little more like that. So I don't have to do anything on top to get that. But on bottom I do. I don't like that plus 5 there. So, if you think about the direct comparison test, if I want to show it converges, then I need to make sure that this is less than or equal to something that converges. Okay? So if I'm looking for the overall thing to be less than or equal to, I need to find something that is greater than or equal to. So what I know is that 4 to the n plus 5 is larger than 4 to the n. Technically it's greater than, but I'm going to use greater than or equal to. I know that's true. So what I also know is if I take the reciprocal of both sides, that's true. 1 over 4 to the n plus 5 is less than or equal to 1 over 4 to the n. So then further I know that that's true by multiplying by 3 over n. Simple enough. So now I know that this sequence is less than or equal to that sequence. But this sequence right here, since I have the same power on top and bottom, I can rewrite that as 3/4 to the n. Well, if this 3/4 to the n, okay, what can I do with this? Well, I have something to a power. Well, that looks like a geometric series. And in fact, it is. And r is 3/4. And since the magnitude of r is less than 1, this converges. So since this converges and this is bounded, this is an upper bound for that, then if this thing shrinks down to or converges to a finite value, this has to converge to a finite value. So that tells you that it converges. Let's keep on rolling. Now I have natural log of n squared over n plus 1. That's pretty yuck. So in this particular case, what you want to do is you want to say, okay, how can I come up with a sequence that makes this manageable? Well, n plus 1 is not super fun. So what we kind of like is something with 1 over n. So I know that n plus 1 is greater than 1 over n. So I know that that's true. But that's actually not that helpful. That's not that helpful because this is going to diverge. Well, if that's less than that, However, this isn't strictly less than that. This is actually greater than 1. So what do? We say, okay, well this is greater than 1. So I need something where the numerator is greater and the denominator is less. Strictly greater than or equal to, less than or equal to, less than or equal to. So I can't use just n. That doesn't work. But what I can do is say something like 3n, or even in this case 2n. 2n. Right? It's because I know n plus 1 is less than or equal to 2n. If I start at 2, that's 3, but this is 4. If n is 3, that's 4, but this is 6, and so on and so forth. So 1 over n plus 1 is greater than or equal to 2n. Oh, sorry, 1 over 2n. And I know that the natural log of n squared is greater than or equal to 1. So I know that that holds. So then I can say, all right, this sequence is greater than or equal to that sequence. Now, 1 over 2n isn't really a well-known sequence, but if instead I pull a 1/2 out, or I can pull that 1/2 out front, that's the property of series. This is the harmonic series. The harmonic series is well known to be divergent. So since this diverges, this has to diverge, because it's larger. So that one's a little trickier, because what we'd like to do is we'd like to just set this thing up where we kind of throw away we say, oh, well, I'm just going to throw away what's in the denominator, and it's always going to be less than that. You know, this is always going to be, oh, this is always going to be greater than that, so I'm good, or whatever. But in this particular case, I couldn't just do that with n. I would have the inequality in the wrong direction. So one of the tricks you can do is you can take some multiple of n. So instead of n plus 1, you can do 2n. Like if this was n plus 7, you could have done like 8n, right? So if this was n plus 10, you could have done 11n. And a lot of times that's a trick that helps you get what you need in the right direction. A lot of this does come down to some tricks and some experience. So finally we have 3 to the n plus n over 2 to the n minus 2. So in this particular case, what I notice is this kind of looks like a geometric series to me. Like if I just hide those terms, that looks like a geometric series. So what I want to do is I want to say, okay, how do I get there? I have this. Well, the first thing I want to say is, am I trying to prove convergence or divergence? Well, if I look at this, that's going to be divergent, because that's going to be geometric, but 3/2 is larger than 1. 3/2 is greater than or equal to 1. So that's going to be divergent. So what that tells me is I need, overall, that needs to be my inequality direction, right? It's a greater than or equal to. So for the numerator, I can just say 3 to the n plus n is greater than or equal to 3 to the n. Simple enough. In the denominator, I also get something very simple. 2 to the n minus 2 is less than or equal to 2 to the n. Okay. So what that tells me is 1 over 2 to the n minus 2 is greater than or equal to 1 over 2 to the n. So again, when I take the reciprocal, I flip the direction of the inequality. And then since this is true, then we have the inequality we're looking for, which is, and then you have 3/2 of the n. And now we know that that diverges, so that also must diverge. Now you might ask yourself another question. How do I know that this diverges? Because from the definition of the geometric series, this has to start at 0. You're right and you're not right if you say that. You're right in that this has to start at 0 if we want to plug a value in and get the total sum of the series. If this doesn't start at 0, then the sum of the series will be incorrect. But we're not We don't care about the sum of the series. What we're caring about is whether it converges or diverges. And whether it converges or diverges doesn't matter if it starts at 2 or 5 or even 100,000, because we're counting up to infinity. No matter how many terms you think you started with, we have way more terms that we're counting long term. So it doesn't matter where you start. When you're talking about convergence, that doesn't matter. When you're talking about the actual sum, that's when you really care about that starting index.